because I can do this integral for one of the charges, and then for another, and for another, and for another. So one single charge, I can place it inside the surface or outside the surface and see what effect it does, okay? If I have 10 charges, result, okay? All right, so let's do that, okay? So let's consider first the more interesting situation that the charge happens to be inside the surface. Okay, so I'm going to put the charge over here. So let's consider the single charge inside the surface first, okay? And again, I repeat that if we have many charges, all it takes is to do more integrals for each charge. That's obvious. So the other interesting situation is when the charge is outside, okay? So, well, actually that picture is going to be a little bit, so I'm going to do it like this. Okay, something, I think that will work. Okay, so when we do this integral, we need to obtain the electric field at the point on the surface and the area patch. So let's say that I am walking on the surface, and at this instant I am here. So then the way we build, so there is an area patch here. That thing is 1 centimeter squared. Clear? Okay. So the way we define our vector areas, remember, if we have an enclosed surface, our vector area is going to be a vector that is perpendicular to the surface at that point. And if the surface is closed, then it points outward. Okay? And the magnitude of that vector is the area of the patch, which is 1 centimeter squared, whatever it is. So it looks like this. Okay? Now, for this charge, we can use Coulomb to obtain the electric field at that same point, because we need the two to multiply them together. So the electric field will look like this. And it is 1 over 4 pi epsilon 0 times Q divided by this distance squared. Correct? So let's call this distance r. Just for a moment. Of course, that distance r is going to vary from point to point. Okay.
You do the vector term.
What's that?
You can do the vector term there also, right? You would say the vector term is...
Oh, yeah. This is very important in the direction r. Thank you, yeah. Okay. So, when we multiply these two things together, we are going to get 1 over 4 pi epsilon 0 times Q over r squared times the area S. So what I'm doing here is the magnitude of ds, which is the magnitude of the vector ds, which I call ds, the magnitude of this unit vector r, which is 1, times the cosine between the two. The cosine is this thing here. The cosine of the angle is this one, I mean. So that's the cosine of theta. Okay? So I want to look at this thing here. And now let's see what happens, okay? So I have this segment here, and I have this is ds, okay? And this angle is theta. I want to make this construction. I'm going to make a line perpendicular to the electric field through that point. Well, okay, so it's not very good. Like that. And then I will take that area that starts here and then ends here. Okay, of course that the same thing is going to happen in other dimensions, but just at the beginning, to make it simple, imagine that the area goes just perpendicular to this board. And so I'm going to over here and here. Okay, so if the angle is 0, then this construction, now let me see if I can make it a little bit more clear, because that's the central part of the argument. The original area was this one. That's the original area. And now I'm doing these lines that are parallel to the direction of the electric field to produce this new area here. Okay? So, you see this is the angle theta. If theta was equal to 0, meaning that if the area and the electric field were in the same direction, how would those two areas compare?
In the same direction.
If ds and E are in the same direction. Yeah, of course, if this perpendicular would be 0. But I'm asking, how would they compare if this is 0? If this is 0, so forget about where that charge is. Say that ds stays the same. E.
It'd be the same.
Yeah, so they would be the same, exactly, right? Because it's very easy to see. I have this patch here, and if the electric field and ds are parallel to each other, then the ds and the projection are the same thing. Okay? Of course, it could be another situation where they are perpendicular to each other. In that case, I would get 0. Okay? All right. So, a little bit better, if we do a little bit of trigonometry, somebody can help me with that. What is this area? This one. This one I know is ds by construction. But what about this one?
Yes, cosine squared theta. Cosine squared. Plus sine theta.
Just worry about the line for now, and imagine, just to make it simple, that the other part of the area is perpendicular to the board. So only need to worry about what is, in other words, for now, it's enough to answer, given this length, what is the magnitude of this length here, the one that I just... It's just simple geometry.
So that's, yes, cosine theta.
Okay.
Does the magnitude shrink as E gets more perpendicular to ds?
Yes, exactly. Yeah, of course, because if E and ds are perpendicular to each other, this line will shrink to 0. When theta is 90 degrees, it will go down to 0. Okay? And when theta is equal to 0, very clearly the two are the same. Okay? So, okay, it takes a little bit trigonometry, but it's obvious from these two statements and the fact that they are lines perpendicular to each other that this line is perpendicular to E, and this line is perpendicular to ds. So if ds and E make theta, the two lines perpendicular also make theta. So, okay, so the question now is a sine or cosine, but it's obvious it's a cosine, because when theta is equal to 0, we get full magnitude, and when theta is equal to 0, etc. So if you can look in more detail, but it's easy at this stage of your careers to see very clearly this ds cosine theta. Okay. Very, very good. So look at what we just discovered. That this new area is ds cosine theta. Okay? So this thing that I just highlighted here, ds cosine theta happens to have a geometric meaning. It is the, if I consider the point Q that generates the electric field, and now I think in the concept that we just talked about a few minutes ago, where I put my eye and I observe the moon, this tilted segment, okay, I'm happy that you are smiling now, because this tilted segment, look at this guy here, okay? All of you far away will see the full magnitude of this pen. But if I do this, you will see no magnitude at all, okay? Abstracting a little bit, of course. But, and then as I change that, that angle, you'll see more and more of it. So turns out that from the point of view of Q, this is the original moon, maybe, and this is the magnitude of the moon as seen from Q. Wonderful. Okay, so now, so this is the projection we were talking about, going from, for example, 3 dimensions to 2 dimensions. In this case, no. In this case, we still go from 2 dimensions to 2 dimensions, but we are talking about what we really see of that patch. Okay? Do we see the whole thing, or we see less area because it's tilted? That's what we are talking about.
We need to know the angle as well.
Well, we'll see. So turns out that this ds cosine theta altogether is the vision that we have from Q. That's the important thing. Okay? Yeah.
Okay, so ds is two-dimensional?
ds is two-dimensional, sure. It's the patch on the surface. So what I'm trying to get at is how is that patch seen from Q? Okay? If the angle is 0, then we'll see the whole thing. But if the angle is 45 degrees, it will be shrunk by what? By square root of 2, right? By the cosine of 45 degrees. So this is that patch. Very good. Now, I'm going to do the following. This distance from here to here is r. Okay, I call it r. So let me erase because I need room, but remember that's r. So what I'm going to erase q also, but remember it's there. So what I'm going to do, center at q, I'm going to draw a sphere, okay, a circle in the plane of radius a. Small, okay, so I'll tell you how I do it. This is going to be a sphere of radius a. And I will choose it in a very simple way. I will take A so that this is completely enclosed in the surface S, like in the picture here, okay? So that nothing sticks out. I can always do that. Okay, and then I will consider this construction. I will take that point of the surface, and this point, not of the surface itself, but the projected surface, that ds cosine theta patch, okay? That there is going to, of course, in 2 dimensions, 2 points, but in reality, it's going to be some boundary there. And from the boundary that I see, from that boundary, I'm going to draw a line to my eye, another line to my eye, etc. So I'm going to produce a cone there, okay? And that cone in 2 dimensions would look something like this. Okay? And now, of course, it's getting small, but I think you can still see it. That cone will intersect the smaller sphere at a patch itself. And that patch that is small, it has to be small because already ds is a small quantity. So this patch is also even smaller. But doesn't matter. It looks like a little circle in there. In that case, it's a perfect circle. Doesn't really matter how complicated this ds is. This is a circle because I built that on a surface, on a sphere, I mean. Okay? Fine. So my question now is, if this sphere has a radius a, and the distance from Q to the surface is r, I want you to tell me what is the ratio between this patch over here on the sphere and ds cosine theta. How do I write that thing? Okay, go ahead.
It's going to be the length of the patch of the sphere over a squared.
Okay, okay, fine. So let me write it, okay? So So this is going to be the length on the sphere. Let's use a different letter for the element of sphere. Let's call it ds on the sphere. So let's call it dsa because it has a radius a. That over
A squared equal to ds cosine theta over.
Okay, very. This is precisely the same kind of, yeah, that's correct, the same kind of similarity that we used before. We started with the lines, now we went to the areas, and now from the picture, we realize that the area on the sphere divided by the distance to the patch, which happens to be the radius of the sphere by construction, is equal to ds cosine theta, which is the perpendicular dimension that we care about, divided by the distance to that patch. Okay, wonderful, we understand that. So then this ds cosine theta is nicely divided by r squared. So that means that we can write this thing as 1 over 4 pi epsilon 0 q, and then instead of writing this ratio that we have here, I'm going to write this ratio here. ds over a squared times ds, but now on the sphere. Okay? Now, this construction, of course, can be done anywhere on my surface. And clearly, I can go out of the plane, although it would be difficult, impossible to draw. But I don't really need to restrict myself to here to the plane. I can do it in 3 dimensions. And everywhere I go on that surface, I will land on the sphere on a little circular patch all the time. Okay. So that means that is sort of a change of variables. Now what I'm doing, every time that I have to do an integral on that real surface, I'm going to move it to an integral on the sphere. Okay? So now we can do this. And we can do this, and then we can do the integral. We change variables. Okay, now we went to the sphere, and so this is an integral on the surface of the sphere. Okay, what is dsa for a sphere?